Hello and welcome to Zoom into Physics, a monthly intellectual excursion into interesting topics. Even though our beings are locked down, our minds can roam free. My name is Scott Martin. I'm the soon-to-be deposed chair of the New South Wales branch of the AIP, having almost served out my 2-year sentence. And meanwhile, I am still gainfully employed with the CSIRO, where I lead the Applied Physics Group. Long before the formal subject of astrophysics, thousands of years ago, the people of the Darug Nation sat here in Dee Why, I imagine, and looked up into the night sky with a deep curiosity about what they were seeing. That curiosity and fascination with the world, and especially the stars, transcends the ages and probably ever will. I acknowledge those traditional astrophysicists of the lands on which we're meeting and pay my respects to the elders past and present. Tonight our topic is the dark side of the universe. Our universe is dominated by the dark side, the dark matter, the dark energy, and those have shaped the evolution of the cosmos, or have they? We'll find out tonight. We're going to tackle one of the biggest mysteries facing physics, the nature of that dark side. Hordes of astronomers and particle physicists are making observations, designing new experiments, and concocting theories to try to shine light on the dark matter and dark energy. I think this topic is a really profound one, and so it's fitting that we start with a reading from the good book. And that is, in the beginning, the universe was created. This has made a lot of people very angry and been widely regarded as a bad move. It goes on with some more helpful advice. If you really need to know, all you need to really know for the moment is that the universe is a lot more complicated than you might think, even if you start from a position of thinking it's pretty damn complicated in the first place. I think that's true, and we'll come on to that as well. And then this good book gives us a little bit more advice. It says, there is a theory which states that if ever anyone discovers exactly what the universe is for and why it is here, it will instantly disappear and be replaced by something even more bizarre and inexplicable. There is another theory which states that this has already happened. There is yet a third theory which suggests that both of the first two theories were concocted by a wily editor of the Hitchhiker's Guide to the Galaxy in order to increase the level of universal uncertainty and paranoia, and so boost the sales of the guide. I think this area of science possesses such a strong resonance with the Hitchhiker's Guide to the Galaxy, and I really think Douglas Adams had such an accessible way of conveying the mind-boggling complexities of the universe. I personally approached tonight's topic with an overwhelming sense of ignorance, and I thought in preparation I should try to address this a little bit if I were not to appear to everyone to be a complete ignoramus. However, I found the learning process to be an utter delight, because unlike normal pursuits in which the more you learn, the more you discover you don't know, with dark matter and dark energy, I found that the more you learn, the more you discover how much everyone else doesn't know. And at the culmination of a couple of hours on YouTube, I can confidently say that I've just about achieved a state of unknowing of professorial proportion. I've also concluded that page for page, I think The Hitchhiker's Guide to the Galaxy contains less fiction. Anyway, perhaps in the interest of intellectual discourse, I should probably stop attacking the topic and get on to introducing the panel for tonight. So firstly, let me introduce the three pan-dimensional beings of the panel. We have the philosopher Tibor Molnar, the experimentalist Kirrily, and the theoretician Geraint. And I will ask each of them to introduce themselves. And our opening question for this evening is, what question puzzles you the most about dark matter or dark energy? And let's kick off with Tibor. Let's hear a little bit about you, please.
Thank you, Scott. I'm Tibor. The name is Hungarian. I was born in Budapest a long time ago. I'm an associate at Sydney University in the philosophy department, and I'm actually a philosopher of science. That's where I play. Excuse me. And well, I'm fascinated. The question is, what puzzles me the most about it? Well, everything puzzles me about the dark side of the universe. I'm with Scott. I've got a superior qualification in ignorance in this area. And what I find puzzling is that it doesn't fit with Einstein's theory, and at the same time, Einstein's theory works so well. It doesn't fit with the standard model, and yet the standard model works so well. It doesn't fit with just about anything we know, and yet there's something going on which is utterly mysterious. Now, if that's not puzzling, then nothing is. That's got to be the most exciting subject in town. It's got to be the best game in town. So yeah, I'm looking forward to hearing from the experts, and luckily we have a few extras as well, as Scott will introduce. So I'm hoping that my ignorance will decrease exponentially as the evening wears on.
Thanks, Tibor. Kirrily, can you introduce yourself to us, please?
Yeah, thanks, Scott. So I'm Kirrily Rule. I am the Honorary National Secretary of the Australian Institute of Physics. So that's how I've joined this panel. But I'm an experimental physicist. I work for the Australian Nuclear Science and Technology Organisation in Sydney, so ANSTO. I'm a neutron scatterer, and I am way out of my depth tonight. I, like Scott and Tibor, I have jumped on YouTube and I've jumped on the internet and done a lot of research. And I think that at the moment, my page of questions of what I don't know is far longer than the page of, oh, this is what we do know. So I think if I were to choose one of the questions on my list that's sitting here on this screen, it's to do with the expansion of the universe. So we understand that the universe is expanding. What I'm learning is that that dark energy is causing an exponential expansion of space-time of our universe. So everything is stretching. So what does that mean? Am I getting longer? Am I getting taller? Is atoms getting pulled apart? Or is the gravity holding that bit together? And therefore, are we creating holes in our universe? And what's going into these holes? You know, the whole stretching and expansion of the universe, it blows my mind. I just don't get it. So if I can learn a bit more about that tonight, I would really appreciate it. Thanks.
Awesome, thanks, Kirrily. And Geraint, finally, our third panel member, if you would like to introduce yourself, please.
Okay, so my name's Geraint Lewis. I'm a professor of astrophysics at the Sydney Institute for Astronomy at the University of Sydney. And look, I'm in my element tonight because I work in the fields of dark matter and dark energy. I do theoretical explorations of what dark matter and dark energy do to the universe. I also do observational studies to hunt out how much dark matter and dark energy there is. And of course, I suffer from that thing that all scientists do, in that in my day-to-day job, I walk around and I talk about dark matter, dark energy, la, 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 la. And then when I'm lying in bed at night and I start to think, what are these things? I suddenly get a cold chill, right? Because as Tibor pointed out, we have these dominant bits to the universe, and they just don't really fit with our current theories. And so, you know, I just think, well, maybe they are just stuff to be discovered. But then I also have this nagging doubt that maybe we've just got everything all wrong. And, you know, it just sits at the back of the mind. So yeah, it's my area, but it still makes me very uncomfortable.
Thanks, Geraint. I think that being a professor in astrophysics is probably the coolest job title there is on the planet. When you've got to fill in at any form and it says occupation, you've got a professor of astrophysics. That is the coolest.
Sorry, can I add one tiny point there? So there's there's the important difference between an astronomer and an astrophysicist. So if you're ever at a party and you've got somebody that you want to talk to, you say that you're an astronomer because that draws people in. If you're at a party and you've got somebody you don't want to talk to, you say you're an astrophysicist because that drives people away. So that's the important difference.
let me also interrupt. There's only one job description that I think will top the Professor of Astrophysics. A colleague of Bill Phillips, who's Australia's Nobel laureate, works at the National Institute of Standards and Technology in the States. He builds the world's best atomic clocks, accurate to 18 decimal places. And these clocks are used to measure the rotation of the Earth, which varies by up to a millisecond a day, plus or minus. Every time you jump up and down or you erect a tall building, the ballerina effect comes into play and the Earth slows down and speeds up and wobbles about. And for GPS and for satellites and internet connections and so on, we need very accurate clocks. So there's a fellow down the corridor down the corridor with these atomic clocks who works in one of the laboratories. There are 3 of them around the world. There's one in Paris and one in Japan. And these 3 establishments with their multiple atomic clocks determine what the time is. They measure the rotation of the Earth and they work out exactly what time it is, and they set the time for universal time. And the job description, the business card of this fellow, who I don't know his name, but he lives down the corridor from Bill Phillips. His business card says he is the director for Earth rotation.
That's pretty cool.
And for me, that's a winner. You can't top that one. That's a winner for me.
Someone who used to be based on my side at Linfield is the CEO of the National Measurement Institute, and he's in charge of the time, similarly, the time standard for Australia. So he calls himself the Time Lord.
Okay.
Tonight we have an embarrassment of riches when it comes to professors, and so let me introduce Tamara Davis, another astrophysicist from the University of Queensland. A long-standing relationship with the AIP. In 2011, she was the Women in Physics Lecturer Award recipient, where she toured around the country and gave many lectures to school children and physicists alike. And according to her Wikipedia page, she competed for Australia at an international level in ultimate frisbee. So tell us a little bit about yourself, Tamara.
Hi, yes, thanks for the introduction and thanks for having me along. I am indeed a cosmologist, and I did do that lecture tour at the AIP way back a decade ago now, which was super fun and a really great way to chat to lots of people about physics and the stuff that I research, which as Geraint, just similarly to Geraint, I study dark energy and dark matter. I find that I think that there is, even though there's a great mystery about what they are, there is a huge amount of knowledge out there about how they behave and their properties. And that's one of the things that I try to help generate. And because I do a lot of studies of studying the universe and trying to measure the properties of dark energy. Like Kirrily was asking about the expansion and the acceleration of the expansion of the universe and how that works. So I've measured that using supernovae and the distribution of galaxies and the bending of light by gravitational bodies in the intervening sort of distances. And there is so much we know about them because we can just see their effects so clearly in such a huge variety of ways that all come together and give us the picture of how they behave. But the question remains is, what are they? And so that's the thing that I'm studying and trying to figure out, and the thing that sort of gets me up and gets me to work every morning. And then, yes, I do occasionally run around big grass fields chasing round discs of plastic as the way to keep me fit and keep my body and brain healthy while trying to figure out the cosmos.
Thank you, Tamara. And our second guest is Professor Ray Volkas, who's a theoretical particle physicist from the University of Melbourne. Again, a long-standing relationship with the AIP. In 2017, he was the recipient of the very prestigious Harry Massey Medal. So please, Ray, tell us a little bit about yourself.
Yeah, well, hi, everyone, and thanks for the invitation to this august panel. So as well as being a theoretical particle physicist and professor at Melbourne Uni, I'm also chief investigator on an entity called the Australian Research Council Centre of Excellence for Dark Matter Particle Physics, which has been going for a year or so. So this is a 7-year well-funded centre with an experimental program, a theoretical program, which I'm involved with, multi-institutional, multi-state. And we're trying to do our bit to perhaps uncover at least some more information about the nature of dark matter. So my day job is to invent new theories of dark matter and to explore their consequences for regular particle physics, also early universe cosmology, obviously. So some overlap with Tamara there, and occasionally for high energy astrophysics. So I'm what they call a model builder. I like to take the standard model of particle physics and add bits to it to explain things like dark matter. And in my free hours, as you can see from my background, I like to play that thing.
Thank you, Ray. So before we kick off, let me just say a couple of comments of how it works. Basically, the only really strict rule that we're working under tonight is that we'll finish about 9:30, and how we actually get there is largely up to us, as long as we remain in the vicinity of the topic. Everyone is welcome to participate with the questions and comments. Either unmute yourself and pitch in, or post comments, questions in the chat function. Often there's a little sort of side channel going on in the chat, so please feel free to get in there, and or everyone can read it and then sort of introduce that into the discussion. Just please remain courteous, because this is a very hot topic where people can get a bit riled up, and of course be excellent to each other. So our starter for 10 here is definitions. That's where physicists love to start any talk. So let's start off with, what is it that we're talking about? We've got lots of people who could open that one for us. So please, somebody take us on that journey. What is dark matter and dark energy, and why do we even have to think about it?
Well, even before we start that, may I ask a question from Tamara? Tamara, you said that we know quite a lot about what these things do. What I'd like to ask is that assumes that there is something out there doing it. What I'd rather like to do is ask you whether it, at the moment, with our current understanding, it wouldn't be perhaps more correct to say we know an awful lot about what we need something to do, but we actually don't know if it's out there doing it. We don't even know that it is, let alone what it is. So I'm wondering if we're not already assuming too much, and I'm hoping that the answers to Scott's question just now is going to perhaps tell us a little bit about why we think there is actually something like that, rather than just saying we need something to do the things that we see because it's just not working for us.
I think the definition of what dark energy and dark matter is actually answers your question quite nicely, because my definition of those are the names we give to whatever is causing the effects that we see. Now, that cause does not have to be a thing. Like, we often speak of dark matter as potentially being a particle. It could be that we need a different theory of gravity to explain what we're seeing. So there's not like a substance, a thing out there that dark matter is. It could be a variation in the theory. Now, for reasons that Ray and others will probably tell you as well, we think that one probably is a particle, but dark energy is a bit more ambiguous, particularly, and we really don't know whether that one is, a thing or a substance or some sort of different theory, or is there something else that we haven't thought of, or there's still always the possibility that we've just interpreted the observations incorrectly, even though there are so many different ones that's getting more and more difficult to explain. So yes, I think the dark energy and dark matter are just the names we give to our uncertainty, the names we give to our lack of knowledge. And we're trying to explain what is causing the observations we see. But that could be a whole range of things, including many things non-substantial.
Okay, so I understand that, and I agree with you. My reason for asking is not because I thought it might be otherwise, but rather because I think it's important for us physicists to be careful about what we say when we speak to the general public, because they're going to misunderstand us. If we say there's something out there doing something, because that's just the way we speak about it, they're going to think there's a particle out there, or they're going to think something which we in fact don't yet know. So I wonder if we're not overstating our case and misleading the general public and making them even more confused than they already are, or maybe more confused than we already are, in the way that we speak about these things. So I think the language matters for the purposes of science communication.
May I chip in? So, you know, what excites me about the topic of dark matter in particular is that the observations that we call the dark matter problem prove that our current theories of the fundamental physics, which is comprised of the standard model of particle physics for all the non-gravitational forces that we know about, and general relativity for gravitation. What the dark matter problem, as we call it, says is that those two theories, when you combine them and try to understand cosmology and also astrophysics, that they don't work. So what the dark matter problem proves is that there exists what we call new physics. There's something that we have to change about our current physical theories in order to accommodate the data. In the case of dark matter, it's most likely some kind of particle. It could be primordial black holes as well, but that's also pretty exciting. Modifications of gravity are I think, less likely. So, you know, we can say, according to our present thinking, it's most likely a particle of some sort or a set of particles. But for sure, for absolute sure, there exists some form of new physics. And I personally, a priori, I don't care if it's a modification of gravity or it's a new particle or it's primordial black holes. They're all exciting to me.
I think that's a good description, Ray, is that it's just new physics. You know, I think what Tibor was saying, if we're trying to make it an object that we can sort of hold in our hands, then we're getting into tricky waters. But to define what it is out there, perhaps we need to define what observations we have. Let's get to something concrete that we can understand. What's happening? What's gravitational lensing? What's happening at the outer edges of the galaxies? What are we observing?
Indeed, indeed. I would just comment on that, you kind of indirectly make a good point. We shouldn't jump to conclusions. So in the particle physics community, and to some extent in the astro community too, I think, a lot of people think that dark matter is something called a WIMP, a weakly interacting massive particle. It's a particularly simple dark matter candidate that some people think is well motivated from a particle physics point of view. And I have heard people at conferences sort of convinced that dark matter is a WIMP, and that if you don't think it's a WIMP, then you're kind of a little bit soft in the head or something. And I do object to that because there is no direct experimental evidence at the moment that the dark matter is that particular favored candidate by many people. So I do think we should keep an open mind about what this new physics is. Most likely a particle, but as to what kind of particle, there's a huge range, a notoriously huge range of what it can be.
Can I add just a tiny comment on top of that? I mean, Tibor's point is right about the language, and when Tamara and myself and Ray, etc., get together and we talk about dark matter, we already understand what that phrase encompasses. The problem is when you talk to the media is you can't put footnotes in, right, about what we mean when we say this particular phrase. They simplify and chop things down. So the message about the uncertainty or the range of possibilities as felt by physicists often gets lost when it's presented to the general public. So I don't think it's purely our fault that there's a confusion out there, because when we speak about this, we know what we're talking about. It's when somebody else writes about it that there's more certainty put on one idea over another.
The thing that there is no doubt about is that there is something out there that needs to be explained.
Absolutely.
So, you know, there are observations that we can't explain with our current theories. So I guess should we start talking about what some of those observations are? Because
great idea. Yeah.
Kirrily was just asking. So one of the earliest things for dark matter is basically, so my analogy for how we first saw dark matter and some of our greatest evidence for it is it's due to the motion of galaxies. And so it's invisible, but you can see it by the way it moves things around. And so my analogy is like, if you look outside and you see the leaves of trees blowing around in the wind, you can't see the wind, but you can see that the leaves of the trees are moving, and you can infer that something is pushing them around. Now, we don't, if you go back 200 years, we didn't have, a particle theory of matter that we have today. We didn't have the periodic table and that kind of thing. And so over the last few hundred years of science, we've learned what particles are and what the wind is. And now we're sort of in that state with dark matter. Now we can see the galaxies being pushed around and moved in a way that we can't explain. And we're trying to explain why they do. Now, one of the coolest thing that I think is that dark matter was like blindingly obvious, basically, as soon as we knew galaxies were galaxies. Go back into the 1920s, and people were having these arguments about whether these spiral things that you could see in the sky were like clouds of spiral gas really close to us, or galaxies, which was not the word they used then, but galaxies really far away. It turns out that they're galaxies far away, and as basically, as soon as we could measure the distances to them, and we measured that the universe is expanding, that most of these galaxies are moving away from each other, the first measurements of galaxies in clusters, where you could see the galaxies orbiting themselves, could show that the galaxies were just moving way too fast to hold themselves together against like the with just the mass that you could see in the visible part of the galaxies. And that was first announced in like 1931, and the expansion of the universe was 1927 ish. Basically, it's been blindingly obvious that there was something out there that was weird from very, very early days. That was like one of the first pieces of evidence.
And I add that one of the things that most impresses me about our understanding of dark matter is that if you simply take our current theories, which is what I was talking about earlier, the Standard Model and general relativity, and you add to it one component, a certain kind of dark matter, which we call cold dark matter in the literature, then you can understand everything from the dynamics of clusters of galaxies, like Tamara was talking about, to the rotation curves of spiral galaxies, to gravitational lensing, which hasn't been mentioned yet, but is very relevant, and also the general growth of what is called large-scale structure in the universe from the Big Bang onwards. So large-scale structure means galaxies and clusters and all these things. So the idea is that the universe immediately after the Big Bang was very smooth, very homogeneous. And then over the course of time, primarily through the action of the attractive force of gravity, over density is bunched up, and eventually we get galaxies and stars and so on. And in order for that to work, you need dark matter in there. You need dark matter. You need the gravitational effects of dark matter to make that work. And the amazing thing is that the type of dark matter you need to add in to understand all those astrophysical things that Tamara was talking about, it's exactly the same thing that helps you understand the evolution of all the large-scale structure from the very early universe onwards. And that concordance of a simple hypothesis explaining actually two quite different things, actually a whole set of different things, is to me very impressive, and which is why I believe that the dark matter hypothesis is usually stated as some kind of massive something or other, particles, black holes or whatever, that it's really on the right track.
Can I check in a little point here as well? So behind Kirrily, of course, is a simulation of structure in the universe. Right? So this is somebody's simulation where they've set up a chunk of the universe and they've watched the evolution of the universe over 14 billion years and watched how matter clumps together into galaxies, etc. If we left out the dark matter component and try to evolve the universe based upon only the stars and gas that we can see, we just do not end up with a universe that looks like the universe around us. So there's all the clues of just looking at individual objects, about the rotations of galaxies, the dark matter in clusters, gravitational lensing. But then there's the overall evolution of the universe over 14 billion years. Dark matter and dark energy are imprinted on the universe we see around us. And that to me is sort of like incredible evidence that something is going on.
Indeed, one of the biggest evidences for dark matter is that big things exist. Because if you look at how rapidly things could grow without dark matter from the background that we see, so we can see the cosmic microwave background, which is the afterglow from the Big Bang, and we can actually measure how clumpy the universe was, like certainly the normal matter in the universe was back just about 380,000 years after the Big Bang. And so in the 14 billion years since then, you can calculate how fast things would have fallen towards each other under gravity if it had started from that initial condition. And you can't have made anything like the structures that we see today just by from that initial state that we actually have seen the universe in. So that's just the fact that there's large galaxies and clusters of galaxies now is a simple piece of evidence for dark matter. One of the simplest pieces of evidence for dark energy is that stars are close to 14 billion years old, and just the age of the universe. When we used to think that the universe was slowing down because gravity should slow it down, before we discovered that this expansion is actually speeding up, there was a problem with the age of the universe and the age of the oldest stars. So the universe was predicted to be about like 9.5 billion years old based on the expansion rate of the universe that we could see and how much that expansion should have decelerated over time. And people who studied stars were like, hold on a second, we can see stars, we've measured like how they should evolve, they should be like a few billion years older than that. So, you know, people thought it was a problem that the stars were older than the universe that contained them. And that was solved by the discovery that the universe has accelerated to the rate that it is at the moment after an initial period of deceleration. And that meant that the universe was actually older than we thought, which means that the stars are younger than the universe, and hooray, that works. So just the age of the stars is also another piece of evidence for the age of the stars combined with the expansion rate of the universe we see today is another piece of evidence that dark energy is out there.
And can I also say that, to come back to dark matter, that our knowledge of dark matter has really changed a lot over the 35 years I've been doing research. Back when I started, and even somewhat later, back less than 30 years ago, it was still possible that the dark matter could be in the form of massive neutrinos. So neutrinos are these charge zero elementary particles that pervade the whole universe, according to the Big Bang theory. And if you gave them, and in the Standard Model, as most simply constructed, they're massless particles, like photons of light are massless particles, something that's allowed by special relativity. But anyway, if you gave them a bit of a mass, not much mass at all, but a little bit, then that, you know, looked like a very economical and reasonable explanation for what the dark matter is. And so big experiments were done at CERN, for example, in the early 90s to look for neutrino dark matter. And they ruled that out. And then the cosmologists ruled it out because when galaxy surveys and so on were done with sufficient statistics, it became clear that that form of dark matter didn't work. It cosmologically couldn't explain what you see behind Kirrily's head. It just doesn't work. It's something that we call hot dark matter, and that's ruled out. Hot means that the neutrinos, when structures started to form, were moving around very quickly at close to relativistic speeds. And we now know that dark matter has to be pretty cold. That is not moving very fast at all when structures started to form. So, you know, we are learning things about dark matter. We certainly know things that dark matter can't be. And I think that's important.
Okay, can I ask a question then? One of the observations that have just been explained is the radial velocity curve of rotating galaxies. And we know that the stars near the outer rim of the galaxies are rotating or are spinning around the galaxy too quickly. And by centripetal force, they should be flung out rather than being held in, because there's not enough gravity to hold them in place. So I understand how that works. So there's something holding them in place. Now, if I look at something like one of Tamara's frisbees, the particles in the frisbee are held together by electromagnetic particles, photons, if you like, but they're held together by some kind of glue. And now that they're glued together, when the frisbee is thrown and it spins, yes, the outside of the frisbee turns too fast and gravity isn't enough to pull them in, but it doesn't matter because something else is holding them in. So am I correct in understanding that one of the roles that this dark matter has to play is the role of that glue that holds a galaxy together when it's spinning? Is that a reasonable way to think of the dark matter particles, as in sort of there's some sort of boson that that acts like a glue that holds the galaxies together and maybe holds everything together?
Tam, go ahead.
I was going to say it's a little bit tricky to call them glue exactly, because if they were acting like a glue in the same way as a frisbee does, where it like is gripping on you would need a different force as well, I believe. So that, but there are plenty of theories out there where you propose a new type of force that would hold particles together in a different way. So that's a possibility. If we want to use the forces that we know and love, then just adding a particle that has mass is good enough for gravity to do the job. If it was a really fixed, strict gripping in the way that a frisbee does, like a frisbee rotates rigidly, the galaxies don't rotate rigidly. Sure. They move in lots of pieces. So there's, so it can't be exactly like that. Okay?
Okay, so there's two ways to think about it then. One of them is that it's a force particle, and the other one that it's a matter particle. And what would be the difference in each of those? Maybe after Ray's had his say, that will be my next question as to how we might understand it in each of those ways.
Well,
I might answer. I might also add a third possibility that it's neither of those particles, and the law of gravity just works differently at different distances.
Yes, of course.
Right?
Yeah. So the usual view of dark matter is not that it's a force-carrying particle, but that it's a massive particle or set of particles of some sort, and the force involved in holding spiral galaxies together and explaining their rotation curves is none other than standard gravity. So if you like, the glue is gravity, but the glue needs a source, and that source and the luminous matter that we see, stars and gas and so on, is insufficient to provide enough gravitational attraction to explain the rotations of spiral galaxies.
Okay.
I actually have a question for Tamara and Geraint about dark energy. It's sometimes said that dark matter is pretty weird, but dark energy is really weird. We really have not the faintest idea what it is, and yet Einstein's cosmological constant at the moment fits the data very well. Mm-hmm. So, what's your reaction to that? I know there's a lot of quibbles about the size of the cosmological constant, but the fact that there is a cosmological constant to me is not that big a surprise.
Is that for me to go first?
Yes, you can.
Yeah, look, again, this is one of these things that keeps me up at night and really bothers me, is that just to get people on the same page here, when Einstein was first thinking about the universe, he thought the universe was static and unchanging. He wrote down his cosmological equations and found that they predicted the universe was expanding or contracting. So he added this term, which we now call the cosmological constant, which acts as an anti-gravity to balance the gravitational pull of the universe and make the universe static. He discovered soon afterwards from the observations of Hubble, etc., that the universe was expanding. So this term was discarded, and he said it was his biggest blunder. But at the end of the 90s, when it was discovered that the universe was accelerating and we had this stuff called dark energy, it was realized very quickly that the properties of this thing that we call dark energy is exactly the same as the cosmological constant as written down by Einstein. The big problem is that the cosmological constant is a weird term in terms of the mathematics, in that it's one of these things that can sit on one side of an equation or the other. And on one side, it's something physical and it's a substance and it's in the universe. And on the other, it's related to space-time and curvature. And the fact that dark energy looks like this term that Einstein uncovered, to me, tells me that it is something important about the universe. And it's not what astronomers want to hear, because we want to know if dark energy is a substance that we can get our hands on and we can map out and see if it changes and evolves, etc. If it is Einstein's cosmological constant, it becomes the most boring universe, because the cosmological constant is that it's constant and then changing, and it is not something we will ever get our fingers on. So yeah, it bothers me. And in fact, it gets even worse than this. There is a lovely article by Ofer Lahav and Lucy Calder from a few years ago that showed that you get exactly the same cosmological constant by doing Newtonian cosmology, by considering the universe just under Newton's laws. And so to me, it is a worry that everything looks like this cosmological constant. But I'm a natural worrier anyway. So I'm going to go over to Tamara to give us an upbeat view.
Okay, I'm an optimist, or was saying, and if it is the cosmological constant, I think that that's actually quite nice and elegant and a simple solution. That this thing that we didn't necessarily expect it to be there, but maybe that's just the way that gravity works, and we don't need to look for any deeper explanation. But it's sort of, in a way, it's sort of unsatisfying. It's like you do want to explain, gravity appears to be acting in reverse. And I'm not sure if we've explained this very clearly, but what dark energy is doing, it's accelerating the galaxies away from each other. Something is causing, we think, gravity to push, not pull. And that's like super weird. That's like if I took a ball here and I threw it up in the air, it accelerated off into space. But it only happens at really large scales. So the thing that Geraint said about the term being on one side of the equation or the other, if it was on it's not just how gravity works, but it's on the other side where it's related to the matter and stuff of the universe, that's where it gets to the point that Ray was talking about, of where people disagree on the magnitude of it, because on that side, and I noticed in the chat, someone asked about the Heisenberg uncertainty principle. There is a prediction from quantum physics that the vacuum, emptiness of space, like if you take out all of the particles and stuff like that, and we can debate the exact definition of vacuum, but if we try to evacuate as much as we possibly can, it's not actually possible to take out all of the particles, these virtual particles. There's energy left over, even if you take out everything from the vacuum. So there was, and it just so happens that the properties of that would cause the expansion to accelerate. It would have a repulsive gravity effect. And so but the prediction for how much of that stuff there should be is wildly wrong, depending on who you ask, somewhere in the order of 60 to 120 orders of magnitude wrong, which could make it, apart from infinity, is one of the worst ever predictions of physics for the matching to experiment. But is that something that we need to be explained? And one of the reasons I'm really interested in measuring dark energy more precisely to try and understand it is because maybe this is the hint that we need that's pointing us in the right direction for the next theory of physics. Maybe we need a quantum theory of gravity in order to explain why the vacuum energy takes the value it does, which is so different to that predicted by our standard model of quantum physics. And so maybe there's really something fundamental here that we can, if we can explain it, we can understand the next depth of level of all of our physical theories. And that's quantum gravity is something that traditionally lacks experimental probes that can test it. And so this might be one of the things pointing us in that direction, which is why I find it, one of the reasons I find it really interesting.
Tamara, about the Heisenberg uncertainty principle, do we think that our ideas of dark matter are such that virtual dark matter particles pop in and out of existence as well as all the other ones? Is it a particle like all the others as far as the Heisenberg uncertainty principle is concerned? And is that also true for dark energy?
Ray's probably the best person to answer this, but if it's a virtual particle, I believe, or if it's like a WIMP, for example, then I think all of those particles should be able to be produced as virtual particles. Ray?
Yeah, I mean, in the standard hypothesis, or the standard suite of hypotheses about what the dark matter is, a particle or a set of particles, those things would obey exactly the same laws of quantum physics as electrons and quarks and so on. And so you would have some of them as real particles, and that's what we see, you know, astrophysically and cosmologically.
Okay.
And then they would also play a role as virtual particles in very subtle particle physics processes happening at the quantum level.
Okay.
And that's something that's worked on. I mean, the quantum effects of dark matter particles as virtual particles is an active field of study in the literature.
Now, we know all the other particles can interact with their antiparticles and so on, and eventually decay or be disassembled into photons. Dark matter particles presumably won't do that because they're somehow not electromagnetic. Is there something there that I don't understand? There's a lot in there I don't understand, but what sort of particle could it be? It's clearly not a particle which is electromagnetic like all the other standard particles, is it?
That's true. I mean, the simplest hypothesis is that the dark matter, whatever it is, and don't think of it necessarily as just one species of particle. It could be a set of particles.
Sure.
You know, if it has any electric charge at all, then it's really tiny, right? So probably it's zero, but it's not ruled out that it has some really tiny electric charge. But anyway, you happen to have hit on what I work on in my dark matter research, which is whether the dark matter particle is its own antiparticle or it isn't. And I'm rather fascinated, and have been for many years, with the concept of what's called asymmetric dark matter, which is the idea that there's dark matter and dark antimatter, and that just like ordinary matter and antimatter in the evolution of the early universe annihilated into photons and neutrinos, so also the dark matter and dark antimatter annihilated into some form of radiation, and that the dark matter that's left over is left over for the same reason that we have any matter at all in the universe, and that's because there was a bit more matter than antimatter created at some point, a really tiny amount more, 1 part in 10 to the 10, more ordinary matter than ordinary antimatter was created at some point in the early universe. This is one of the big mysteries of particle physics and early universe cosmology. Yeah. And the hypothesis is that maybe the same thing happened in what we call the dark sector, you know. So yeah, that's an active field of research, not as active as it was a few years ago, but I really like that hypothesis, and I'm trying to get it to work really, really properly. So far, it doesn't work 100% properly, but you know, I think I could argue that it has less problems than other candidates. Maybe, I don't know. Maybe I shouldn't be so bold.
Okay, so what would be the nature in your model? What would be the nature of that radiation that dark matter and dark antimatter would decay into? Because again, it can't be electromagnetic, can it?
No. Well, yeah. Well, good question. Excellent question. Some years ago, about 10 years ago, there was tantalizing evidence from cosmic microwave background analyses and so on, that there was something called dark radiation. So when physicists and cosmologists talk about radiation, they just mean relativistic particles. So photons and also neutrinos most of the time. They're just moving at speeds close to the speed of light. That's what radiation means.
Yeah.
And the radiation content of the universe is very important for driving the expansion of the universe at early times. Not now, but at early times. And there was evidence, and I was very excited by this, for the existence of dark radiation. So if you accounted for all the photons and all the neutrinos, there was evidence, there was some tantalizing evidence, not very statistically significant, but tantalizing, that there was an additional component. And that would have fitted like a hand in a glove for these kind of theories, because it could have been that the dark matter and antimatter annihilated into its own dark photon or dark neutrinos or something like that. And that was the dark radiation. Unfortunately, the evidence has largely gone away. And now when you invent these theories, and this is one of the things I struggle with, you have to figure out if really there were dark matter particle, antiparticle annihilations. They had to mostly go into ordinary radiation. And you have to figure out exactly how that would happen. It's one of the headaches of this kind of theory.
Okay, I could see the headache.
I'm going to chuck in an extra point here as well. So one of the things which a lot of physicists and astronomers are looking for, there is this possibility that dark matter interacts with itself and it does decay into things that we can detect. So there's been excitement now for a couple of decades where people have looked for gamma rays, high energy photons, from places where dark matter might be self-annihilating. So you need places where dark matter is very dense. So the centers of galaxies, so especially the center of our own Milky Way, there's a signal of excess gamma rays from there. People are hunting for gamma rays from centers of dwarf galaxies, etc. Anywhere where you might think dark matter has piled up, because that increases the chance of dark matter interacting with dark matter. And there's been a bun fight for 5-10 years over the emission that we see from the center of our Milky Way, whether or not that is consistent with the exciting potential that it could be dark matter self-annihilation, or the boring signal of just everyday astrophysics, which is pulsars, right? Pulsars produce high energy radiation. So it is a very active area. Because we don't know what the dark matter particle is, and we just assume that it interacts weakly, right? That doesn't mean only via the weak force. There could be decays into things that we can detect. So people are looking for it, but at the moment, the places that we look at are places where there are lots of stars and gas and all those other confounding factors that make any experiment difficult. There's never a clean signature, but we're looking for it.
Okay.
So, Geraint, maybe we can explore that a bit more. I mean, what sort of experiments are they proposing, or people are trying to measure it? I mean, it's here now, right? In us, around us, and what are the chances that they're gonna find it? What's the best chance we've got to discover this stuff? And then I think there was a really fascinating chat that you were answering as well, which you might want to bring out, which was about the expanding universe and the constant density. And what does that mean? Does that mean the mass of the universe is going up, right?
Okay, so I'll touch on some of this because I think our other guests here are more experts. So firstly, there's two issues here. There's dark matter and dark energy, right? So with regards to dark matter, there are a lot of physicists considering the potential interactions that would reveal dark matter to us. Now, you mentioned it's here, it's in this room, and I'm going to, if you cup your hands together, like so, given what we know about roughly the particle physics, inside there should be of order 10 dark matter particles. So you sort of think that I've got it, right? I've got the 10 dark matter particles in my hand. But the problem is that they don't interact with your laboratory experiments. But there are very sensitive experiments being built around the world to try and do direct detections of dark matter. So there's a number in the US and Europe. There's a famous set of experiments in the Gran Sasso laboratory in Italy. I think it was the Italian-Swiss border, that kind of area. And I'm going to turn to Ray because there is a copy of this experiment being built here, or not a copy, I should say, but a related experiment being built here in Australia, in Victoria, at the Supple laboratory. So I'll let Ray talk about that, and then I'll come back to this notion of dark energy, which doesn't dilute. So Ray, do you want to mention about Supple, etc.?
Yeah, sure. An exciting development for the national community. So first of all, to uncover the particle nature of dark matter, which is what the Center of Excellence I'm part of is trying to do, we need to get lucky. We need the dark matter to interact with ordinary matter a little bit non-gravitationally. If it only interacts gravitationally, then there's no kind of experiment you can do to kind of really uncover its particle nature. It needs to have some sort of very subtle way of interacting with ordinary matter, which we would use as a dark matter detector, in order for us to get some information about its particle nature. And these interactions have to be very weak, so that they don't spoil the observations we have about dark matter being very weakly interacting and not shining and all the rest of it. But this is entirely possible, and in fact it would be rather surprising if the only interactions dark matter had with ordinary matter were gravitational. The real question is, how strong are these non-gravitational interactions? So we need to get lucky, and so we're looking. So in a town called Stawell, west of Melbourne, about a 3-hour drive, go to Ballarat and keep going, similar distance. That's where the Stawell Gift is run, the barefoot handicap sprint is run. Anyway, they have a pretty deep gold mine. At its deepest, it goes down 1.5 kilometers. And it's a very convenient mine. I've been down once. I like going down mines, it's good fun. Because you can just drive in. You don't have to take an elevator. I've been down those sort of mines as well. But this one you can just drive and you get into a minibus and you kind of drive down the spiral in the sort of labyrinth underground. And about 1 kilometer under the ground is being built the Stawell Underground Physics Laboratory, or SUPL. It's under construction right now. I saw a picture just last week of the frame of the lab, being constructed. Special floor was put in. You need special sealing on the rock, because when you're searching for dark matter, you have to block out all sorts of other processes that fake the appearance of dark matter, but aren't actually dark matter. We call these backgrounds, and radioactivity is a background, and we need to shield that out as much as possible. So the way these experiments are done is you have a slab of something. In the case of this experiment, it's called sodium iodide. And sodium iodide, of course, is made of atoms, and atoms have nuclei. So the hypothesis is that a dark matter particle will occasionally come along and interact most probably with the nucleus of either a sodium or an iodine, possibly also with the electrons, but most likely with one of the nuclei. And the nucleus will for no apparent reason, suddenly get a kick. So, it's like you've hit a billiard ball, a cue ball on a billiard table, but you can't see the cue. It just suddenly, the cue ball shoots off. And so you would infer the existence of a very weakly interacting invisible particle that came along and in a very rare process kicked a nucleus. So we're looking for these nuclear recoils. And you need to be deep underground because you need to shield from cosmic rays, which can also cause these background processes. Neutrons are a big problem. So neutrons, are neutral particles that exist in the center of nuclei, and the collisions of neutrons with nuclei look an awful lot like the collision of dark matter with a nucleus. So you need to make sure that what you're seeing is not really neutrons. Geraint mentioned the Gran Sasso lab, which is actually due east of Rome. So it's not on the Swiss border. It's near a town called L'Aquila, where they have earthquakes occasionally. Anyway, it's a rather large underground lab. I've actually never been there. I hope to at some point. And there's an experiment there called DAMA, D-A-M-A, which for a long time now has had controversial evidence for possible existence of dark matter. What they see is what's called an annual modulation. So the idea is they have their detector, sodium iodide, also, and as the Earth revolves around the sun over the period of a year, sometimes the detector is moving into what we call the dark matter wind, and sometimes it's moving in the same direction as the dark matter wind. And this changes the rate you would expect for dark matter nucleus collisions. And so what you should see is a bunch of events, a signal that has a periodicity of exactly 1 calendar year, and it has a certain phase. So meaning that the crests and the troughs occur at a certain time, because we understand the Earth's motion through this hypothetical, dark matter halo. And their observations clearly show an annual modulation. The statistical significance of it is ridiculous. It's like 13 standard deviations. They certainly see something, and the phase that they see is also consistent with a dark matter signal. So the reason this is a puzzle, we're not jumping up and down and saying we discovered dark matter, is because there are a whole bunch of other experiments that have not corroborated them. These experiments are done in many different ways, all using dark matter nucleus collisions as the fundamental process, but they're done in different ways. They're not all looking for this annual modulation effect. Anyway, to cut a long story short, there are a whole bunch of experiments that contradict Dharma, at zeroth order. So what we're, not me personally, but my colleagues are trying to do down in Supple is put an improved version of the Dharma detector. It's called SABRE, S-A-B-R-E. And it's an improved version. The crystals will be more, the sodium iodide is a crystal, they'll be more radio pure, fewer radioactive contaminants. Everything will be made of radio pure stuff. So the sensitivity should be higher than the Dharma experiment. And the fact that it's done in the Southern Hemisphere is also important, because there's no question that Dharma has seen an annual modulation. The only question is what it's due to. And because their results contradict a bunch of other experiments searching for dark matter, the suspicion is that there's some very unusual, subtle, unknown background process that we don't understand that happens to also cause an annual modulation. It might have something to do with the summer-winter cycle, because the phase I was talking about matches pretty precisely with the summer-winter cycle. And in the Southern Hemisphere, of course, we're completely out of phase with the Northern Hemisphere in terms of summer and winter. So if it really is a seasonal effect due to some weird background, we should see it with the opposite phase in the Southern Hemisphere. So this kind of experiment has never been done in the Southern Hemisphere. So we wait with bated breath. They're constructing the detector now, they're constructing the lab. Hopefully it will all be in place by early next year. And then in 3 or 4 years or something like that, there should be enough data to check Dharma.
Fascinating.
Can I ask a question about the experiment then? If you say it's about a 3 to 4 year collection, is this something that you just set running and you just hope for the rare events and then add them all up at the end of 3 to 4 years?
Yeah,
it's constant.
Yeah. You have photomultiplier tubes around. You have various detectors. There's a veto system to get rid of stray neutrons flying around. Don't ask me all the technical details about the detector. It's beyond my pay grade. But basically, yes, you would see some background events that are consistent with nuclear recoils, and you simply plot those events as a function of time. All right. Yeah.
And what do you expect? What do you expect? A difference, a phase shift being in the Southern Hemisphere?
The funny thing is that—
Sorry, I've put you on the spot there, Ray.
Well, I try to be as unbiased as possible. So I just want them to do a good experiment and a believable experiment and a very sensitive experiment, and to contribute to try to resolve this Dharma mystery, because it's a genuine mystery. Dharma has seen something. The dark matter interpretation is problematic, but they have seen something. And it's not like the community is clueless about possible backgrounds. All sorts of backgrounds have been studied to death. Cosmic ray muons coming along, knocking out neutrons, and the neutrons mimicking dark matter. All these calculations have been done, and none of them can explain this annual modulation in terms of its magnitude, because it's quite a large effect. So it's a genuine mystery. Even if it turns out to be, so Geraint said before that neutron stars are boring. That's interesting. They're not that boring. But you know, even if it's a boring background effect, it's a background effect we've never seen before. So there's something fishy going on. We don't know what it is. It is a genuine mystery. And I know the people at Gran Sasso, who are not involved with the experiment, really want to get to the bottom of it.
Well, it'll be interesting, even if there is a phase shift and it's the other way around and you find out that it isn't dark matter, it is something else. Even that's going to give you some new physics because there's something else to work out. So even
yeah, God knows what that is. I mean, it's a funny thing. But by the way, this is not the only such experiment being done. There's one in Korea as well that already has results, and there's one in Spain. So there's some competition around. So, you know, our people feel quite a bit of pressure to get this thing built and running.
Did Korea see anything?
No, they haven't seen anything yet, but they don't quite, as I understand it, they don't quite have the sensitivity yet to rule out Dharma on their own.
Right.
Yeah, and as from the astrophysicist point of view, like these kinds of experiments are really important because, like, you know, going back to the tree analogy, we didn't explain what air was by watching the leaves of trees blow around. And there's a good chance we're not going to explain dark matter by watching the motion of galaxies. We need to figure it out from a theoretical and experimental perspective as well. And Geraint, you mentioned, you know, if dark matter is a particle, then you've got about 10 here. I was once sold a box of dark matter. Oh no, I have to take off my background if you can see this. It's a box of dark matter. You can see it contains 0.2104 grams of dark matter. And it's got all the ingredients on the back with the of how much, what it's made up of how much dark matter, dark energy and stuff are in this box and stuff. So there you go. You
That's
can buy
brilliant.
a box of dark matter.
That's brilliant.
Wonderful.
Yeah.
How do you stop them getting out?
Well, as far as I know, whenever they get out, they get replenished again.
Yeah, more come in, sure.
Yeah.
So I would like to ask my two more gravitationally oriented colleagues, Geraint and Tamara, what they think of primordial black hole dark matter.
But wait, 1 second. Did you mean chubby? Are you calling us chubby, Ray?
No. No.
Oh yes,
Not Tamara.
Yes. Sorry, Tamara, please.
Primordial black holes. I'm intrigued by the possibility of primordial black holes still. There is not that. So the idea here is that dark matter is not a particle, but it's lots of tiny little black holes floating around, or like sort of intermediate size, like pretty small, but yeah, black holes basically. And they could have been generated in the early moments of the universe and be floating around and be causing some of the dark matter effects that we could see, but we still wouldn't see them. We just see them by their gravitational effect. Now, there's a few bits of evidence that push against this being a possible theory. One, their effect that they could have had on the early universe, like the cosmic microwave background. The other most obvious one is there's an upper limit on how many of these there can be in certain mass ranges by the fact that when a black hole passes between us and a star in our galaxy, for example, it would briefly magnify the background galaxy because it would lens the light, and just like a normal lens that you get when you look through your glasses or something like that, it would magnify it, it would make the background source brighter. And we don't see the stars in our galaxy randomly just flashing and becoming brighter and fainter all the time. So we can put an upper limit on how many black holes are floating out there milling around with the normal stars in our galaxy. But that said, there's still a sort of a parameter space of black hole masses and things where it is possible for some contribution to the dark matter to be coming from these black holes. And it isn't quite as ruled out as I would like it to be able to say that, no, that's not the solution.
Do these primordial black holes accrete matter? Are there things falling into them?
Mm-hmm. Yeah, so if we were in a really dense environment, you'd also expect these things to glow because the matter that falls towards black holes gets hot. Mm-hmm. But in the general dilute atmosphere of the galactic medium, you don't expect too much of that.
they wouldn't have grown to anything significant over 14 billion years?
They can, and these things that we're looking for, like some of the mass ranges, you can actually have stellar mass black holes that are floating around out there that could be causing this. So we're not talking like super tiny. We could, there is a wide range in which they could be.
Okay, so they can be up to stellar mass. Okay.
Or even heavier. And in fact, the microlensing, which is what we call it when a black hole passes between us and the distance in the star, the microlensing constraints are very weak on higher mass black holes, because you could have a big contribution to the gravitational effect by a small number of large black holes as compared to many, many small black holes. If it was a small number of large black holes, the chance alignments of them and distant stars would be very rare. So we can't really rule that out by the number by not seeing it. Whereas very smaller black holes we can rule out, but then once they get too small, the magnifying effect would be insignificant.
Yeah, so you need a very long duration microlensing observational program, right?
Yeah.
And if you had too many of those little black holes, then they would in fact cancel each other out. You might get a compensating effect, and it would wash itself out in the as the light arrived to us, because one thing would bend it one way, the next one would bend it the other way. So maybe you could even, if you had too many of them, the effect would cancel out. Would that happen? Would the microlensing effect cancel out if you had too many of them?
If they are really, really small, but then you almost start heading back to them being particles again, and there's no real difference. But there are other effects that kick in if you've got black holes wandering around, right? They do things like disrupt star clusters, and they cause all kinds of dynamical effects that people are looking for, whether there are black holes scattered through globular clusters. And as Tamara was saying, the windows where black holes could make up an appreciable amount of dark matter are closing. There are some ranges left, but lots of them are now closed. So it's sort of less favorable. It would be kind of weird if the window that we haven't probed yet is the one in which all the black holes are sitting. But yeah, every plot I see, the parameter space is just being scribbled out left, right, and center.
Okay.
Yeah. I think if you fill in all of the non-scribbled out bits, like the bits that remain possible, that have not been constrained yet, you would need to basically fill everything perfectly if you wanted to explain all of dark matter just with black holes. So the likelihood that, yeah, they're exactly in the places that we haven't seen is extremely small. So, but I expect black holes to contribute some amount of sort of dark matter effects.
In a lecture I saw by Kieran O'Hare, he drew one of those diagrams where he coloured in all the bits that have been ruled out, and he ended up with very little in the end of what mass these dark matter particles might be. So he's eliminated quite a large amount of parameter space even there.
Mm-hmm. Yeah.
Oh, but don't forget, physicists are very good. If you can rule down parameter space, but then just put a new dimension in and expand it in another direction, you've got a whole range more of parameter space to explore.
Yeah, that's true.
Yeah.
Except you need to have some excuse for making up another dimension, don't you? You need to say
not you have to be careful. Dimension means a different thing when I'm talking to my physicists. Another parameter, another direction to exploring. So
yeah, okay,
yeah.
As opposed to a multiverse.
As opposed to a multiverse, yes. We should save that topic for another day, actually.
Okay.
I noticed we're approaching time, and so there was that question raised in the chat, and I'm going to punt this straight back to Tamara here about the weird behavior of dark energy, that dark energy doesn't dilute as the universe expands where other stuff does. Mm-hmm. So do you want to just tell people a little bit about what that means for the history of the universe and what it means for the future of the universe?
Yeah, so that's one of the interesting features of dark energy, and one of the reasons that Einstein's cosmological constant is such a good explanation of what we're seeing, in that despite the fact that normal matter, if you expand, the density of that matter goes down. So you've got a certain number of particles, they're spread out over a bigger range, the density is now lower. As you expand the universe, the density of dark energy does not go down, as far as we can tell. It remains constant throughout the universe, throughout time, and in all positions, which is in contrast to dark matter as well, because dark matter clumps around like galaxies and things, and it does dilute as the universe expands. And that's one of the reasons where early on I alluded to the fact that the universe was originally decelerating and then started to accelerate. Now, one of the ways we saw this was like looking at distant supernovae and using them as standard candles. And by measuring how bright they are, we can measure how far they are away. And the furthest away ones, the light has taken a long time to reach us. So we can basically look directly at how fast the universe was expanding back then compared to now by looking at how fast these supernovae are moving away from us. And because we know the distance, we can track that quite precisely. And we can see that it's now accelerating, but also that it was decelerating. And the reason for that is when the universe was young, the observable universe was much smaller. Everything was much more clumped together. And when that was the case, the attractive force of gravity on the dark matter and normal matter was winning, and that was slowing down the expansion of the universe. But then as the universe expanded and those features became more dilute, the effective, like attractive gravity from them got weaker and weaker and weaker until we hit the point where dark energy had a bigger repulsive force than the rest of the matter had an attractive force, and that's when the universe started accelerating. So the dark energy has just been hanging out in the background, waiting for its chance to take over and say, no, I'm in charge now, and everything move away. And so that's one of those things. But I think one of the things that was in the chat was that about I think, was there something there about the conservation of energy and stuff as well? It's like if you have, it's sort of like you're adding energy to the universe when you do this, because the total energy density changes over time. And that's really weird. And I could give like an hour-long talk on just the energy conservation in the universe, but maybe that's another one for another day. I don't know. I should invite.
Well, that was going to be my question. How do I make sense of the conservation of energy law, given that we're adding more energy as the universe expands, or we're not adding, but there's more
it's filling in the gaps.
There's more dark energy because there's a bigger universe for the dark energy to occupy. But if that's a difficult question, I'm certainly happy to give it another session. I'd love to hear that one.
You all froze for just a second, so I didn't actually get all of your question, but I think you were saying, yes, explain it a little bit. Is that right?
Well, either that, or if it's too hard, then yes, let's do another session. I'll hand that one back to Scott.
Yeah. Well, I'll give the very brief answer that in the expanding universe, you don't necessarily need to conserve energy because it's not, but energy is conserved at every infinitesimal point in space, but it's impossible to define a volume in which you can define energy to be conserved. And part of that's due to relativity and people's different perspectives in relativity, because if you're moving, you disagree on what is simultaneous. So I can't agree with my friend who's zipping past me at close to the speed of light what the density is over there, because we don't necessarily agree on what now is. And that's one of the reasons that we can't do that very well. But energy is always conserved at every infinitesimal point and in every interaction. So,
but if we have a view from nowhere, if we're outside the universe, the energy should be conserved, should it not?
So sorry, can
I know it doesn't make sense to ask that question.
So Tibor, why do you think energy has to be conserved?
Oh, only because that's what I've been told by everybody. That
precisely, exactly the same reason why kids think the sun is yellow. It's what you've been told.
Well, we do have conservation laws, obviously.
We do, but conservation laws are written in a particular mathematical framework, in a particular setting, and the universe has its own setting in which there is no overall conservation of energy law.
Okay.
I'm currently teaching relativity to my fourth year class, and they always sort of gasp when I tell them that energy is not conserved, because it's been drummed into them from their first science class that energy is conserved. Sorry, Tam, you were going to say something.
I was just going to say that the actual reason that we expect energy to be conserved in some situations is a really beautiful philosophical concept. So it's called Noether's theorem, after the mathematician Emmy Noether, and you get conservation of energy when you have time symmetry. So if the laws of physics work the same forwards and backwards, basically you have time symmetry, and that in those situations you expect conservation of energy. You get conservation of momentum if you have spatial symmetry. So the laws of physics work the same over there as they do here. And you get conservation of angular momentum if the laws of physics look the same no matter which direction you're watching. And the problem with the time symmetry with the universe is not obviously true. And the mathematical term, there's no time-like killing vector in the universe.
Well, of course, there is
everybody.
Of course, there's the other, even deeper philosophical question of how do you get something from nothing? But that's a completely different question. I guess that has to be answered too.
Yeah, but that's also why energy is conserved at every infinitesimal point, because the laws of physics are time symmetric in every interaction. So, yeah.
Tibor, I'm just dying to ask you, why is there something rather than nothing?
Oh, that's an excellent question. I wish I knew.
I think we need
philosophers only know how to ask questions. They certainly don't know how to answer them.
We could definitely spend another hour and a half discussing that one. So we should save that again with the multiverse for a future discussion.
I'm up for that.
Yeah, let's put on the list.
Can I just talk a little bit about philosophy of science in this? And that is the idea of instrumentalism that, that Percy Bridgman came up with, which is how science was done, but he gave a name for it. And so that was to say that there are concepts and objects that we could call scientific objects, like a gene or an electron, that we don't experience in our everyday life. So the positivists who wanted to touch everything and see everything and that you could be sure of. But it seems to me that all the dark arts that we're doing here are the biggest examples of instrumentalism that we've got. But it's really exciting because, there's a kind of psychological thing here, because when you say, well, we want to know what it is, you see, in the end, you have conferences where people discuss what an electron is, because, there's a sort of complacency that we know what it is. But in fact, when all the details come, we're still doing it, we know it instrumentally. We know it through our instruments. In other words, it's all indirect. And we're at a stage, I think, with the dark arts that the data is underdetermined. We haven't got enough data. Like we've got more data on an electron than we have on these dark things. And so it's a matter of time till we get to that sort of psychological complacency that we think we know now what it is, right? But it's still an instrument. People can come, but you only know it instrumentally, don't you? Do you think that's the way we're going?
It's actually both, if I may attempt an answer. It's actually both better and worse than that. It's true, I think, that all science is necessarily instrumentalist. It has to be, because that's the only way. You only ever observe what things do. You never really observe what things are. All observations are of what they do. So we will find out how things behave, but we will never be able to observe what they are. We have to infer what they are from the observations of what they do. So in that respect, our science is going to be forever underdetermined. And I don't think that's a bad thing. I think that's just a fact of life. It's just what it means to observe things, is to look at what things do. You don't observe what things are. We might say it looks like we know we're looking at what they are, but in fact, what we're doing is interacting with them, and those interactions are interactions with what they do as opposed to what they are. So at bottom, I think all science, all physics, all fundamental physics is going to be instrumentalist, and it's going to be all underdetermined. And that's perfectly okay for me. I'm happy with that.
We know how electrons behave, and we call them a particle, but as you say,
Yes,
it's not a particle that
that's
we
right.
can touch. And indeed, we also call them a wave, depending on how they behave. And we realize that they're not a particle in the sense of a ball. there's something slightly different to that at the fundamental level. But we do have a theory that explains their behavior in a way that we don't have for dark matter and dark energy.
That's right, yeah.
And in essence, we're describing them through a series of analogies. You know, you just described it like a wave and like a ball, and then now talk about its spin.
Yes.
You know, it's not actually spinning.
That's right.
But it's a great way to think about this intrinsic property of spin. And you know, with my research into dark matter over the last, you know, week or so, the best way for me to understand what people are talking about is through analogy. And is that all science is, using mathematical models to make analogies?
Yes, and metaphors. There's many people that write about the metaphors of science, that's for sure. The one thing that's really interesting, and when I years and years ago, when all this stuff started being talked about, and I heard in you know, in the back of my mind about dark matter and dark energy, I assumed they were kind of the same thing. You know, they were the complementary. You know, they were like the E equals MC. They were the dark E and the dark M on you know, the equation. But then I found they're actually quite different dark things. You know, and the link between them. Some people do link them a bit, don't they? But mostly they're considered to be quite different phenomena. Is that right?
Yes.
Seems like it. But there are people that want to link them, aren't they? I mean, serious people, not.
There are people. Yeah, there are people that think about theories where dark matter and dark energy interact with each other directly. It's usually motivated by. Correct me if I'm wrong, my colleagues, but. You know, one of the interesting things when we know about ordinary matter, we know about dark matter, we know about dark energy. And if you look at the universe today, it's about, you know, 20% dark matter, 5% ordinary matter, 75% dark energy, more or less. So these numbers are not that different from each other. It's factors of 5 and 3. So, you know, maybe they all, you know, interrelate somehow. That's kind of the motivation as I understand it.
And if you could relate them and just say there's somehow two sides of the same coin, you've just reduced the number of things you need to worry about, right? You just have dark stuff that is dark matter in one place and dark energy in the other. But, you know, we know that kind of drive for simplification doesn't always work. But as Ray was saying, at some level, it's a dream for some people, and other people just think, no, these are quite distinctly different things.
I've been sitting here listening to this amazing romping conversation and thinking to myself, how am I going to interject into that to finish on time? And now we know the answer to that. I think we'll have to draw it to a close there. We do have another session that's penciled in for the 22nd of September. I think we'll have to go away and have a little conference about what topic we're going to have based on this. There's a lot of unfinished business, and we didn't cover very much of the plan that we had. So there's so much to say. It's very, very, very exciting. So
maybe we can continue this next time. And
maybe, yeah.
There's more work to be done on the dark side.
Yeah. So it's just up to me to thank our three regular panelists, Tibor, Kirrily, and Geraint. And a really, really huge thank you to Tamara, sorry, and Ray. Thank you very much for joining us today. It's been a tremendous romp through through this. I thought that we were going to have a little bit more contention about whether dark matter is the best theory, and that's probably something for the next session as well. So thank you very much. We'll get this video up onto YouTube as well, so that you can view it and then retire on the tremendous revenue that it brings us all in. Okay, thank you everyone, and stay safe, and see you in about a month's time in lockdown.
Lovely. Thanks a lot, Scott. Thank you, everyone.
Thank you. Good night.
Thanks.